Hello there, and welcome to Sleepy Answers. Tonight, we're drifting into one of the most profound mysteries humans have ever contemplated. A question so fundamental that it sits beneath every other question we could possibly ask. What is reality? Are you truly here reading these words, or could everything you've ever experienced be something else entirely? Something constructed, designed, perhaps even simulated. As you settle in for this journey, I invite you to let your mind wander through these ancient corridors of thought. If you find value in these explorations, a like or subscription helps others discover this quiet corner where big questions meet gentle contemplation. But for now, simply relax. Let the weight of the day fall away. And let's begin by asking a question that might change everything you think you know about existence itself. The question of reality is not new. It has haunted philosophers, mystics, and now scientists for thousands of years. But something shifted at the end of the 20th century. A film appeared that would crystallize this ancient philosophical puzzle into a single vivid image that an entire generation could grasp immediately. The image of someone waking up from a dream that had consumed their entire life. The realization that everything they thought was real was actually something else. A simulation. A carefully constructed illusion designed to keep them contained, controlled, asleep. That film, of course, was The Matrix, and while it was science fiction, it posed a question that science itself has begun to take seriously. What if our reality, the universe we inhabit, the consciousness we experience, is not the fundamental base layer of existence? What if we're living inside something built by someone else? Tonight, we'll explore this question from every angle. We'll journey through ancient philosophy and cutting-edge physics. We'll examine the mathematical arguments that suggest simulation is likely, and the equally compelling proofs that suggest it's impossible. We'll peer into the quantum realm, where reality itself seems uncertain until observed. And we'll ask what it would really mean, if everything we know is not quite what it seems. Before we can understand modern simulation theory, we need to travel back through time. Because the question of whether reality is real is far older than computers, older than electricity, older than written language itself. In the depths of human history, when our ancestors sat around fires and looked up at stars they couldn't explain, they wondered, is what we see the truth? Or is there something more, something hidden behind the visible world? Ancient whispers. Philosophy's first questions. Picture yourself in a cave. Not just any cave, but one where you've spent your entire life. You're chained in place, unable to turn your head, unable to see anything except the wall directly in front of you. Behind you, there's a fire, and between you and that fire, people carry objects that cast shadows on the wall you're watching. These shadows are all you've ever known. The dancing shapes, the flickering forms, these constitute your entire reality. If someone told you that what you're seeing are merely shadows, projections of real objects you've never glimpsed, would you believe them? Could you even comprehend what they meant? This is the allegory of the cave, presented by the ancient Greek philosopher Plato around 375 BCE. It's one of the most powerful metaphors in all of philosophy, and it's essentially an early version of the simulation hypothesis. Plato used this story to illustrate how most humans live in a state of ignorance, perceiving only shadows of true reality. In his view, the physical world itself was a kind of shadow, a pale reflection of a higher realm of perfect forms and ideas. The material universe we touch and see is not the deepest truth. There's something more fundamental beneath it all. But Plato wasn't alone in questioning the nature of reality. Across the ancient world, thinkers arrived at similar unsettling conclusions through different paths. In ancient China, the philosopher Zhuangzi told a famous story about a dream. One night, he dreamed he was a butterfly, fluttering happily through gardens, completely content, with no awareness of being Zhuangzi. When he woke, he faced a disturbing question. Was he Zhuangzi who had dreamed of being a butterfly? Or was he actually a butterfly now dreaming he was Zhuangzi? How could he tell the difference? If both experiences felt equally real while he was having them, which one was the illusion? This butterfly dream cuts to the heart of a profound problem. Our subjective experience, the feeling of being conscious and aware, is the same whether we're awake or dreaming. When you're in a dream, you don't usually realize it's a dream. It feels completely real. You make decisions, have conversations, experience emotions, all of which seem genuine in the moment. Only upon waking do you realize none of it existed in the way you thought. But what if you never wake up from the largest dream of all? What if this waking life is itself a kind of dream, and you simply haven't awakened to the next level yet? In the spiritual traditions of India, this concept is central. The idea of Maya, often translated as illusion, suggests that the material world we perceive is not ultimately real. It's a veil, a cosmic play of appearances that obscures the true nature of existence. According to these ancient teachings, what we experience through our senses is fundamentally misleading. The separation between self and other, the solidity of matter, the passage of time, all of these are Maya, illusions created by consciousness itself. Reality, in this view, is not what it appears to be. Beneath the surface phenomena lies something more fundamental, something that transcends ordinary perception. The Aztec philosophers had a similar concept. They theorized that the world itself might be like a painting or a book written by the divine force they called Teotl. In their metaphysics, what we experience as reality could be something written, something authored, something fundamentally created and maintained by a consciousness beyond our own. Even in ancient Greece, beyond Plato, thinkers like Anaxarchus and Monimus suggested that existence resembled a scene painting, or the strange experiences people have in dreams or states of madness. They recognized that consciousness can be deceived, that what seems solid and permanent might actually be fluid and constructed. Then, in the 17th century, a French philosopher named René Descartes formalized these doubts in a way that would shape Western philosophy forever. Descartes wondered, what if there were an evil demon, a malevolent entity with the power to manipulate all of his sensory experiences? What if this demon created the illusion of a body, an external world, other people, everything he thought he knew? How could he prove this wasn't the case? Descartes realized that almost everything could be doubted. He could doubt his senses, his memories, even mathematical truths if this demon were sufficiently powerful. But there was one thing he couldn't doubt, the fact that he was doubting. Even if all his experiences were false, even if he was being completely deceived, something had to exist to be deceived. This led him to his famous conclusion: I think, therefore I am. The act of thinking, of experiencing consciousness, proved at least one thing, that consciousness itself existed. But beyond that one certainty, Descartes left us with a troubling question. How do we know anything else is real? How can we trust that the external world corresponds to our internal experiences of it? This problem, often called Cartesian skepticism, has haunted philosophy ever since. It's the foundation upon which simulation theory would eventually be built. Because if we can doubt the reality of our perceptions, if we can question whether the world exists as we experience it, then we must acknowledge the possibility that reality itself might be something other than what it seems. What all these ancient thinkers recognized, from Plato to Descartes, from Zhuangzi to the composers of Hindu scriptures, was that consciousness and reality have a mysterious relationship. Our minds create our experience of the world. But does that experience reflect something objectively true about the world? Or does it merely reflect the limitations and constructions of our consciousness? They knew what we still know, that the mind can be fooled. Dreams feel real. Hallucinations seem genuine. Illusions trick the senses. If the mind can be deceived in small ways, might it be deceived in ultimate ways? Might everything be, in some sense, a dream from which we haven't yet awakened? These questions lingered through centuries of philosophy. They took different forms, sparked countless debates, inspired entire schools of thought. But they remained largely abstract, thought experiments that philosophers could discuss without much practical consequence. Then, in 1999, something changed. These ancient questions collided with modern technology in a way that made them suddenly, viscerally real to millions of people. The Matrix arrives. Pop culture meets philosophy. When The Matrix premiered in March of '99, audiences were immediately captivated. The film's groundbreaking visual effects, particularly the now iconic bullet time sequences, were unlike anything cinema had shown before. But beneath the spectacular action, beneath the leather-clad heroes and kung fu battles, was something deeper. The Matrix took the abstract philosophical questions we've been exploring and made them concrete, immediate, terrifying, and thrilling all at once. The story is deceptively simple on the surface. A computer programmer named Thomas Anderson, who goes by the hacker alias Neo, discovers that his entire life has been a lie. The year he thinks is 1999 is actually closer to 2009. The world he knows, the city where he works, the people he sees, none of it physically exists. It's all a computer simulation called the Matrix, created by artificial intelligence to pacify humanity, while machines harvest human bodies for energy. The real world is a post-apocalyptic wasteland, where the few remaining free humans hide in underground cities, plugging their consciousness into the Matrix to free others from the illusion. The film presents this revelation through one of cinema's most memorable metaphors. The rebel leader, Morpheus, offers Neo a choice. Take the blue pill and wake up in his bed believing whatever he wants to believe. The story ends, and he returns to his comfortable illusion. Or take the red pill and see how deep the rabbit hole goes. See the truth, no matter how disturbing it might be. Neo, like most viewers hoped he would, takes the red pill. And what follows is one of the most disturbing awakening sequences ever filmed. He wakes up, not in a bed, but in a pod filled with pink fluid, his body weak and hairless, tubes plugged into his skull and spine. He sees, stretching into the distance, countless towers filled with billions of pods just like his, each containing a human body. Each consciousness trapped in the shared dream of the Matrix. This image, this moment of terrible awakening, resonated with something deep in the collective consciousness. The film became a cultural phenomenon, not just because of its action, but because it articulated a fear, or perhaps a suspicion, that many people had felt but couldn't quite express. What if we're not seeing the full picture? What if there's something more real than what we call reality? The Wachowskis, who wrote and directed The Matrix, were deeply influenced by philosophy. They deliberately incorporated ideas from multiple traditions. The film directly references Plato's cave, Descartes' evil demon, and Buddhist concepts of illusion and awakening. They drew heavily from French philosopher Jean Baudrillard's work on simulacra and simulation, exploring how in modern society, representations of reality have become increasingly detached from any original reality they might have represented. Baudrillard argued that we live in a world of simulations, where images and signs have replaced genuine experience, where the copy has become more important than any original. The Matrix took this concept literally, presenting a world where the simulation had completely replaced reality. The film also engaged with deeper questions about consciousness, identity, and freedom. If your mind can't tell the difference between the simulation and reality, as the character Cypher argues, then what's the practical difference? If the steak you're eating in the Matrix tastes exactly like steak, triggers the same neural responses, creates the same satisfaction, does it matter that it's not real? Cypher, who becomes the film's traitor, decides it doesn't matter. He wants to be reinserted into the Matrix, his memory wiped, so he can live a comfortable life of illusion. Ignorance is bliss, he says, making a deal to betray his companions in exchange for a fantasy life as a rich, important person within the simulation. But the film rejects this choice. Through Neo's journey, the Matrix argues that truth has intrinsic value, that living in accordance with reality, no matter how harsh, is better than living in comfortable delusion. This echoes a fundamental philosophical position that dates back to Socrates. The unexamined life is not worth living. It's better to be Socrates dissatisfied than a fool satisfied. Knowledge and truth are inherently worthwhile, even when they bring suffering. Yet the film also plays with deeper levels of the question. In The Matrix Reloaded, the second film in the trilogy, we learn that even the real world outside the Matrix might not be the deepest level of reality. The machines have created multiple layers of simulation, nested realities designed to control even those who think they've escaped. This nested structure echoes the possibility that many simulation theorists would later explore. If one advanced civilization can create a simulation, that simulated civilization might create its own simulation, and so on, creating layers upon layers of simulated realities, each one thinking it's real. The cultural impact of the Matrix can't be overstated. It gave people a vocabulary for discussing these ideas. Taking the red pill became shorthand for seeing uncomfortable truths. Glitches in the Matrix became a way to describe strange coincidences or déjà vu experiences. The film made simulation theory part of mainstream consciousness. Before The Matrix, talking about living in a simulation might have seemed like fringe philosophy or science fiction speculation. After The Matrix, it became a legitimate question that serious thinkers were willing to entertain. But while The Matrix was reaching popular audiences, academic philosophy was arriving at similar questions through a different route. And in 2003, just 4 years after the film's release, a philosopher would publish a paper that would make the simulation hypothesis respectable in academic circles, that would catch the attention of scientists and technologists, and that would provide a mathematical framework for taking the idea seriously. Bostrom's simulation argument, the mathematical case. Nick Bostrom, a Swedish philosopher working at Oxford University, published a paper in 2003 with the straightforward title, "Are You Living in a Computer Simulation?" The paper's argument was elegant, troubling, and harder to dismiss than most people expected. Bostrom wasn't claiming definitively that we live in a simulation. Instead, he presented a logical argument suggesting that at least one of 3 propositions must be true. And one of those propositions is that we almost certainly are living in a simulation. Here's how the argument works. Bostrom starts with a reasonable assumption about the future. If technological civilization survives and continues to advance, it will eventually develop extraordinarily powerful computers. We can already see this trajectory. Computing power has been growing exponentially for decades. The computers we carry in our pockets today would have seemed like magic to people 50 years ago. If this progress continues, even accounting for potential slowdowns or plateaus, future civilizations could develop computing power that dwarfs anything we can currently imagine. Now, suppose such an advanced civilization developed computers powerful enough to run detailed simulations of conscious beings. Not just simple video game characters following programmed scripts, but genuinely conscious entities with rich inner lives, memories, emotions, the full spectrum of mental experience. These simulated beings would be indistinguishable from the inside from biological beings. They would think, feel, wonder, and perhaps even question whether they themselves were simulated. If creating such simulations became possible, Bostrom argues, advanced civilizations would likely create many of them. Perhaps they'd simulate their ancestors to study history. Perhaps they'd run different versions of their civilization's development to understand how things might have gone differently. Perhaps they'd simply create simulations for purposes we can't even imagine. The key point is that if it's possible and if there's any motivation to do it, they'd likely create not just one simulation, but many. Perhaps billions or trillions of simulated realities, each containing billions of simulated conscious beings. This leads to a striking statistical argument. If there are, say, one real civilization and a trillion simulated civilizations it has created, then the vast majority of conscious observers in existence would be simulated rather than real. If you randomly selected a conscious being from all of existence, the odds would overwhelmingly favor that being simulated. And since you are a conscious being, and you have no obvious way to determine whether you're in the original biological civilization or one of the trillions of simulations, the probability suggests you're most likely in a simulation. This is the core of Bostrom's argument. But he's careful to present it as a trilemma, a choice between three options. At least one of these must be true. First, the vast majority of civilizations at our current stage of development go extinct before reaching the technological capability to create such simulations. Maybe there's a great filter ahead, some existential risk that almost no civilization survives. Nuclear war, climate catastrophe, artificial intelligence gone wrong. Perhaps something we haven't even thought of yet. If this is true, we won't create ancestor simulations because we won't survive long enough. Second, civilizations that survive to develop this technology choose, for whatever reason, not to create ancestor simulations. Maybe there are ethical prohibitions. Maybe it's seen as too dangerous or too morally problematic. Maybe they simply lose interest. Maybe their values and goals evolve in directions we can't predict, and simulating ancestors seems pointless or offensive to them. If virtually all advanced civilizations choose not to create these simulations, then there won't be trillions of simulated realities, and the statistical argument collapses. But if neither of those options is true, if civilizations regularly survive long enough to develop simulation technology, and at least some of them choose to create ancestor simulations, then the third option follows. We are almost certainly living in a simulation right now, because given the vast number of simulations that would exist compared to the one base reality, the odds overwhelming favor any given conscious observer being simulated rather than real. Bostrom isn't saying which of these three options is true. He's saying that at least one must be, and we currently don't know which one. But the implications are striking regardless. Either we're probably going to go extinct soon, or there's some universal reason advanced civilizations don't create simulations, or we're probably living in a simulation right now. None of these options is particularly comforting. The argument caught fire in popular consciousness, particularly in Silicon Valley. Tech entrepreneurs and engineers, people already immersed in creating virtual worlds and artificial intelligence, found the argument compelling. Elon Musk famously stated that he thinks the odds we're living in base reality, the original physical universe, are billions to 1 against. He argued that given the rapid pace of improvement in video games and virtual reality, we are clearly on a trajectory toward creating fully immersive simulated realities. And if we're on that trajectory, why wouldn't civilizations ahead of us have already reached that point? Neil deGrasse Tyson, the astrophysicist and science communicator, has said he gives the simulation hypothesis a 50-50 chance. He's pointed out that the universe seems to follow mathematical laws with remarkable precision, almost as if it's running on code. The fine-tuning of physical constants, the digital nature of quantum mechanics, these things make the universe look, to some physicists, suspiciously like a simulation. Other scientists and philosophers weighed in. David Chalmers, a philosopher of mind, wrote an entire book called Reality Plus, exploring the implications. He argues that even if we are in a simulation, the things we experience are still real in a meaningful sense. The simulated coffee you drink is still coffee, just digital coffee. Your relationships, your experiences, your consciousness, all remain real even if the substrate they run on is computational rather than biological in some deeper sense. But not everyone found Bostrom's argument convincing. Critics pointed out potential flaws. The physicist Sean Carroll argued that the simulation hypothesis leads to a contradiction. If we assume we're typical observers, as the argument requires, but also assume we're not capable of creating sophisticated simulations yet, this creates a tension. If most civilizations fail to create simulations, then we're probably not in one. But if most succeed, then we probably are. The argument seems to require us to be both typical and atypical at the same time. Others questioned whether consciousness can actually be simulated. This goes to a deep question in philosophy of mind. Even if you could perfectly simulate the structure and function of a brain, would that simulation actually be conscious? Or would it be what philosophers call a zombie, something that acts conscious but has no inner experience? If simulations can't actually be conscious, then Bostrom's argument doesn't work, because there wouldn't be billions of simulated conscious observers, just billions of empty simulations. Still others pointed to computational limits. The amount of processing power needed to simulate an entire universe down to the quantum level, maintaining consistency across billions of light years and keeping track of every particle's state might be effectively infinite. Even allowing for future advances, there might be hard physical limits that make such detailed simulation impossible. Physicist Frank Wilczek noted that the laws of physics have hidden complexity that serves no obvious purpose if the universe were a simulation. Why include all this extraneous detail if you're just simulating human experiences? These criticisms are important. They remind us that simulation theory, despite its mathematical elegance, remains speculative. We don't have definitive proof one way or another. But what makes the question fascinating is that it connects to much deeper issues in physics, particularly in quantum mechanics, where reality itself starts to look very strange indeed. The quantum realm, where reality gets strange. To understand why some scientists take simulation theory seriously, we need to venture into the quantum realm. Quantum mechanics, the branch of physics that describes the behavior of atoms and subatomic particles, reveals a reality far stranger than anything our everyday experience prepares us for. And some of its features make the universe look, to certain eyes, suspiciously like it might be computed rather than fundamental. At the heart of quantum strangeness is something called the observer effect. In the quantum world, particles don't have definite properties until they're measured. An electron, for example, doesn't have a specific position or momentum. Instead, it exists in what's called the superposition, a probabilistic cloud of all possible positions and momentums simultaneously. Only when an observation is made does the particle choose one specific state. This moment is called wave function collapse, and it's one of the most puzzling aspects of quantum mechanics. The famous double-slit experiment illustrates this beautifully. When you shoot electrons one at a time through two slits toward a detector screen, something bizarre happens. If you don't try to detect which slit each electron goes through, they behave like waves, creating an interference pattern on the screen as if each electron went through both slits simultaneously. But if you set up detectors to see which slit each electron passes through, the interference pattern disappears. The electrons suddenly behave like particles, each going through one slit or the other. The act of observation seems to change the fundamental nature of reality. This isn't just weird in an academic sense. It suggests that consciousness, or at least measurement and observation, plays a role in determining what's real. Before observation, particles exist in multiple states. After observation, they have definite properties. This led some physicists, including Eugene Wigner, to propose that consciousness itself might be involved in collapsing wave functions. The universe, in this view, requires conscious observers to become definite. Now, consider how this might relate to simulation theory. In a computer simulation, you don't need to calculate everything at once. That would require infinite computational resources. Instead, you calculate what's needed when it's needed. In a video game, for example, the computer doesn't render the entire game world all the time. It renders what the player is currently looking at, calculating detail on demand. Areas the player isn't viewing might exist in a simplified state, or not be calculated at all until the player looks at them. Quantum mechanics looks suspiciously similar. Reality seems to exist in an undetermined state until observation requires it to become specific. Particles have probable properties rather than definite ones until measurement forces them to commit. This looks, to some researchers, like an optimization strategy. If the universe were a simulation, this would be exactly how you'd expect it to work. Don't calculate unnecessary details. Keep things probabilistic until an observer requires specificity. Save computational resources by rendering reality on demand. Another quantum phenomenon that hints at deeper strangeness is entanglement. When two particles become entangled, they share a mysterious connection regardless of the distance between them. Measuring one particle instantly affects the other, even if they're separated by billions of light years. Einstein called this spooky action at a distance, and thought it revealed a flaw in quantum mechanics. But experiments have confirmed that entanglement is real. This, too, looks suspicious from a simulation perspective. In a classical physical universe, there's no reason why measuring one particle should instantly affect another far away. That would require information to travel faster than light, which physics forbids. But in a computational simulation, entangled particles could simply be linked variables in the same program. Change one variable, and the program automatically updates the other, regardless of their apparent spatial separation. No information needs to travel because both particles are ultimately bits in the same computer. Some researchers have pushed this further. Physicist James Gates found what he describes as error-correcting codes in equations describing fundamental physics. These codes are mathematical structures used in computer science to detect and correct errors in data transmission. finding them embedded in the equations of supersymmetry was, to Gates, surprising and suggestive. Why would nature use error-correcting codes unless reality itself were, in some sense, computational? The physicist John Wheeler proposed a concept he called it from bit, suggesting that physical reality might fundamentally be information rather than matter. In this view, particles, energy, space-time itself all emerge from information. The universe would be, at its deepest level, not physical but informational. Quantum bits of information, called qubits, would be more fundamental than the particles and forces they describe. This leads naturally to the idea that the universe might be computation, information processing itself into existence. But quantum mechanics also provides ammunition for skeptics of simulation theory. The computational complexity of simulating quantum systems grows exponentially with the number of particles involved. To perfectly simulate even a modest number of entangled particles requires more computational states than there are atoms in the universe. If the entire universe involves quantum entanglement across vast numbers of particles, as it seems to, then simulating it classically, using the kind of computers we understand, appears impossible. However, this assumes the simulation would be run on an classical computer. What if the simulator used quantum computers? These devices, which are beginning to be built in our own time, exploit quantum superposition and entanglement to perform certain calculations far more efficiently than classical computers. A sufficiently advanced quantum computer might be able to simulate other quantum systems without the exponential resource explosion. But this raises a deeper question. If quantum mechanics is fundamental, if the base reality is quantum, then can it really be considered a simulation? Or is quantum mechanics just another way of saying how reality works, whether that reality is base or simulated? These questions become even more complex when we consider consciousness itself. Because consciousness remains one of the deepest mysteries in science, and some researchers think quantum mechanics might be essential to understanding it. Consciousness, the hard problem. Consciousness is in many ways the greatest mystery of all. We know it exists because we experience it directly, immediately, in every moment. The redness of red, the taste of coffee, the ache of sadness, the thrill of insight. These subjective experiences constitute our entire lived reality. Yet consciousness seems impossible to fully explain in physical terms. How do electrical signals in neurons become the felt experience of existence? This is what philosopher David Chalmers calls the hard problem of consciousness. Traditional neuroscience treats the brain as a complex biological computer. Neurons fire, releasing neurotransmitters that trigger other neurons to fire, creating cascading patterns of activation across networks of billions of cells. From these patterns emerge memory, perception, decision-making, language, all the cognitive functions we associate with mind. This approach has been tremendously successful in mapping brain regions to functions, in understanding how specific types of damage affect specific abilities, in developing treatments for neurological and psychiatric conditions. But explaining consciousness itself, the subjective experience of being, remains elusive. You can describe every physical process in the brain, trace every neural pathway, map every chemical interaction, and still the question remains. Why does all this biological activity feel like something? Why is there an inner movie, a first-person perspective, a sense of being a self that experiences the world? The neural correlates of consciousness. The brain activities associated with conscious experience can be identified, but correlation isn't explanation. Why these particular neural patterns should generate consciousness rather than occurring unconsciously remains mysterious. This is where some researchers have turned to quantum mechanics. If consciousness can't be fully explained by classical physics and classical neuroscience, perhaps quantum processes in the brain play a role. The most prominent quantum theory of consciousness is called orchestrated objective reduction, or OR, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. Penrose approached the question from mathematics and physics. He argued that human consciousness has qualities that can't be explained by computation alone. Specifically, he pointed to mathematical insight, the ability humans have to see that certain mathematical truths are true, even though they can't be proven within formal systems. This relates to Gödel's incompleteness theorems, which show that any sufficiently complex formal system contains true statements that can't be proven using the rules of that system. Yet, human mathematicians can often see that these unprovable statements are true. Penrose took this as evidence that human thought involves non-computational processes. Where might such non-computational processes occur in the brain? Penrose proposed that quantum effects in structures called microtubules, protein structures that form the skeleton of neurons, might be the physical basis of consciousness. Microtubules are small enough that quantum effects could potentially survive there, and Hameroff had proposed that they might play a role in brain function beyond mere structural support. According to OR, quantum superpositions form in microtubules, representing multiple possible states simultaneously. These quantum states orchestrate neuron function, influencing when neurons fire. When the superposition reaches a certain threshold, it collapses through a process called objective reduction, tied to quantum gravity effects. This collapse is a moment of conscious experience. Consciousness, in this view, is the process by which quantum possibilities resolve into classical actuality, mediated by the fundamental structure of space-time itself. The theory is controversial. Many neuroscientists and physicists are skeptical. The brain is warm, wet, and noisy, an environment where quantum effects typically can't survive. Quantum superpositions are fragile, easily destroyed by interaction with the environment through a process called decoherence. In most circumstances, quantum effects disappear at scales much smaller than neurons within timescales much shorter than neural processing. For quantum effects to be relevant to consciousness, they'd need to persist long enough and at large enough scales to influence brain function, which seems implausible in biological tissue. However, some recent research suggests quantum effects might be more robust in biological systems than previously thought. Quantum effects have been found in photosynthesis, where plants seem to use quantum coherence to transport energy with remarkable efficiency. Birds may use quantum effects in their navigation systems, detecting Earth's magnetic field through quantum processes in proteins in their eyes. If evolution has found ways to harness quantum mechanics in these contexts, perhaps the brain does too. A recent study provided some experimental support for quantum effects being relevant to consciousness. Researchers found that drugs affecting microtubules influence how long it takes anesthetics to induce unconsciousness. This suggests microtubules play some role in consciousness, supporting part of the OR theory. But the evidence remains preliminary, and mainstream neuroscience still favors explanations based on classical neural networks. The debate connects directly to simulation theory. If consciousness requires quantum processes, and if quantum processes are hard to simulate, this might suggest we're not in a simulation. On the other hand, if consciousness is computational, if it can emerge from any sufficiently complex information processing system regardless of the substrate, then simulated consciousness becomes plausible, and Bostrom's argument regains force. Some philosophers argue that even if we are in a simulation, our consciousness is real. Chalmers makes this point forcefully. If a simulated person has all the same patterns of information processing, the same functional organization as a biological person, why wouldn't they be conscious? The substrate might be digital rather than biological, but the consciousness would be genuine. In this view, are we in a simulation, and are we conscious, are separate questions. Even simulated beings would truly experience their simulated reality. But others worry about the zombie problem. Could you have a system that perfectly mimics conscious behavior, that processes information exactly as a conscious being would, but with no inner experience? If such philosophical zombies are possible, then perfect simulation wouldn't guarantee consciousness. And if only biological brains can be conscious, then the vast majority of observers in Bostrom's simulated universes wouldn't actually be conscious, and the statistical argument fails. These questions remain open. Consciousness itself remains mysterious, and perhaps that's fitting, because mystery sits at the heart of the simulation question itself. We're conscious beings wondering whether the reality we're conscious of is truly real. The tool we're using to investigate the question, consciousness, is itself the deepest part of the mystery. But while debates about quantum mechanics and consciousness continue, other researchers have approached the simulation question from a different angle, using mathematics to prove, they claim, that we cannot be simulated. The computational universe. Reality as information. Before we examine the arguments against simulation, we need to understand a fascinating idea that many physicists have entertained. The universe might be, at its most fundamental level, information. Not matter, not energy, but bits of information from which everything else emerges. This concept, sometimes called digital physics, suggests reality itself is computational. The idea traces back to the 1960s when computer scientist Konrad Zuse proposed that the universe might be a giant cellular automaton, a system where simple rules applied to bits of information generate complex patterns. Physicist John Wheeler, who coined the phrase "it from bit," suggested that every physical quantity, every measurement, every particle derives from binary choices, yes or no questions answered by the universe. In Wheeler's view, information is more fundamental than matter. Physical reality emerges from information the way a pattern emerges from dots on a page. More recently, physicist Max Tegmark proposed the mathematical universe hypothesis, arguing that physical reality is mathematical structure. The universe isn't just described by mathematics, it is mathematics. Physical existence and mathematical existence are the same thing. We perceive certain mathematical structures as physical because we ourselves are mathematical patterns with the right properties to act as observers. If the universe is fundamentally informational, this lends support to simulation theory. Information can be copied, transmitted, processed. A universe made of information could, in principle, be simulated by processing that information in a different substrate. Your mind wouldn't be able to tell the difference because the information patterns would be identical. Some researchers have looked for evidence of discrete digital structure in reality. If the universe is computed, there might be a minimum resolution, pixels or voxels in spacetime itself. Some theories of quantum gravity suggest spacetime might be quantized at the Planck scale, the smallest possible meaningful length, about 10 to the negative 35 meters. Below this scale, space and time themselves might not be continuous but discrete, like the pixels on a screen. Physicist Melvin Vopson has proposed that information itself might have physical mass, a concept he calls the mass-energy information equivalence. He's suggested that information behaves according to physical laws, including a second law of infodynamics, similar to the second law of thermodynamics but applied to information. According to Vopson, the entropy of information in an isolated system tends to decrease or remain constant, unlike physical entropy which increases. This, he argues, explains why the universe exhibits order and structure, why symmetry is prevalent, why patterns emerge from chaos. Vopson goes further, suggesting this provides evidence for simulation theory. In computer simulations, information is managed efficiently. Redundancy is minimized. Systems evolve toward states that require less information to describe, which is more computationally efficient. If the universe operates according to principles of information efficiency, this might indicate it's being computed. The universe behaves as if it's trying to minimize the information needed to describe itself, which is exactly what you'd expect in a simulation designed to run efficiently. However, this is where recent research has mounted a powerful challenge to simulation theory. Because, while the universe might be informational, that doesn't necessarily mean it can be simulated. In fact, some mathematicians and physicists now argue that mathematics itself proves simulation is impossible. The case against why we might not be simulated. In late 2024, a research team led by Mir Faisal at the University of British Columbia published a paper making a startling claim. Using mathematical theorems, they argued that the universe cannot be a simulation because fundamental aspects of reality cannot be computed algorithmically. No matter how advanced a civilization becomes, no matter how powerful their computers, they could never simulate our universe because reality contains irreducible, non-computational elements. The argument centers on Gödel's incompleteness theorems, one of the most profound results in mathematical logic. In the 1930s, mathematician Kurt Gödel proved that in any consistent formal system complex enough to include arithmetic, there exist true statements that cannot be proven within that system. This was revolutionary. It showed that mathematics itself has inherent limitations. No matter how carefully you set up axioms and rules of inference, you can't capture all mathematical truth within your system. There will always be true statements that your system can't prove. Faisal and his colleagues extended this insight to physics. They argue that a complete description of physical reality requires what they call non-algorithmic understanding. Certain truths about the universe can be known but cannot be derived through computational steps. If consciousness can grasp these truths, as human mathematicians seem able to grasp Gödel's unprovable statements, then consciousness involves non-computational processes. And if reality includes non-computational aspects, it cannot be simulated, because simulation is inherently algorithmic. The researchers approached this through quantum gravity, the attempt to unify quantum mechanics and general relativity. They argue that the fundamental laws of physics, the deepest principles from which space-time itself emerges, cannot be fully captured by computational rules. There's something about the nature of reality that transcends algorithm, that requires intuition or insight, or some form of understanding beyond step-by-step calculation. Lawrence Krauss, theoretical physicist and co-author of the paper, explained that the fundamental laws of physics cannot be contained within space-time because they generate space-time. If you're trying to simulate a universe from within that universe, you face an infinite regress. The simulator would need to exist in some larger reality with its own physical laws, which would themselves need explanation. At the base level, there must be something non-computational, something that just is without being computed by anything else. This argument challenges not just simulation theory, but also the computational theory of mind. If consciousness requires non-computational processes, then creating conscious artificial intelligence, at least through purely algorithmic means, might be impossible. Simulated beings in a computer, no matter how complex the simulation, would lack something essential. They might behave consciously, but they wouldn't be conscious, wouldn't have genuine subjective experience. Critics of this argument point out that it rests on controversial assumptions. The connection between Gödel's theorems and consciousness is disputed. Just because a formal system can't prove certain truths doesn't necessarily mean human consciousness transcends computation. We might use computation in ways that seem like insight, but are actually complex algorithmic processes we're not aware of. The feeling of mathematical intuition might be the output of unconscious computation rather than evidence of non-computational understanding. Moreover, even if our consciousness involves non-computational processes, that doesn't prove the physical universe does. Perhaps the universe itself is perfectly computable, and only consciousness adds something extra. In that case, you could simulate the physical universe, including bodies and brains, but the simulated brains might not generate consciousness. They'd be zombies, empty shells. This doesn't make simulation impossible, just incomplete. There are also practical arguments against simulation. The physicist Sabine Hossenfelder points out that simulating quantum mechanics in detail requires exponentially growing resources. To simulate just 300 particles in perfect quantum detail requires more computational states than there are particles in the observable universe. Scaling up to simulate an entire universe with 10 to the 80 atoms seems computationally impossible, even allowing for future advances. However, simulation doesn't have to be perfect. The simulation might only calculate what's needed when it's needed. Most of the universe could exist in low-resolution, approximate form, with detail rendered only where conscious observers are looking. The simulation might also take shortcuts, using approximations that work well enough for conscious beings inside to not notice. After all, we already know the universe has a resolution limit at the Planck scale. Perhaps that's the pixel size of the simulation, the smallest unit beyond which the programmers didn't bother calculating. Frank Wilczek, another Nobel Prize-winning physicist, offers a different objection. He notes that the laws of physics have hidden complexity that serves no apparent purpose. If you were designing a simulation to create conscious beings and let them have experiences, you wouldn't include all the elaborate mathematical structure we find in fundamental physics. Much of it seems extraneous, unused by anything, just sitting there in the equations. This suggests the universe wasn't designed for efficiency, but is simply how it is, implying base reality rather than simulation. Yet, one could counter that perhaps the simulation includes this detail, because the simulators are studying physics, not just conscious experience. Or perhaps they're using a very general engine that simulates all of physics, and the unused complexity comes along as a side effect. Or perhaps we simply don't yet understand what that complexity is for, and future science will reveal its purpose. The debate continues without resolution. Strong arguments exist on both sides. The question may ultimately be unanswerable from within the system we're trying to understand, which is itself a philosophically interesting conclusion. If we are in a simulation, the simulators might have made it fundamentally impossible for us to prove we're simulated. And if we're not in a simulation, we might still be unable to prove that conclusively. Either way, we're left with uncertainty. But that hasn't stopped people from looking for evidence, from searching for glitches in the matrix that might reveal the artificial nature of our reality. Glitches in the matrix. Looking for evidence. If we are in a simulation, there might be clues, anomalies, glitches, patterns that don't quite make sense if reality is fundamental, but might make sense if it's computed. Researchers and enthusiasts have proposed various ways to detect simulation, though none have provided definitive proof. One approach looks at the structure of space-time itself. If space is quantized, divided into discrete units at the Planck scale, this might be detectable in cosmic rays. The highest energy particles traveling through space should interact with the quantum structure of space-time, causing tiny but measurable effects on their energy and trajectory. Some researchers have proposed looking for anomalies in the cosmic microwave background radiation, or in the distribution of galaxies that might hint at underlying grid structure. Another idea focuses on the fine-tuning of physical constants. The universe seems remarkably well-suited for life. The strength of gravity, the mass of the electron, the cosmological constant, dozens of parameters all fall within narrow ranges that allow stars, planets, and chemistry to exist. If any of these values were slightly different, the universe would be lifeless. This fine-tuning could be explained in several ways. Perhaps there are many universes with different constants, and we obviously find ourselves in one that permits observers. Or perhaps there's some deeper theory that explains why these values must be what they are. But another possibility is that someone tuned these parameters deliberately, adjusting the simulation to produce interesting results. Some people point to déjà vu as potential evidence. That strange feeling that you've experienced this exact moment before, that the conversation you're having has already happened, might be a glitch where the simulation loops or replays events. Of course, neuroscience has prosaic explanations for déjà vu involving memory processing errors. But if you're already suspicious of being simulated, such experiences can feel like momentary glimpses behind the curtain. Synchronicities, meaningful coincidences that seem too perfect to be chance, are sometimes interpreted as evidence. The Swiss psychologist Carl Jung was fascinated by synchronicity, events connected by meaning rather than causation. If you're thinking about an old friend and they suddenly call, or you keep encountering the same number in unrelated contexts, these might be either coincidence, selective attention, or evidence that reality is authored rather than random. In a simulation, coincidences could be easy to arrange, especially if the simulators want to send subtle messages or leave clues. The physicist James Gates, mentioned earlier, found error-correcting codes in equations describing supersymmetry. Error-correcting codes are mathematical structures used in computer science to detect and fix corrupted data. The fact that they appear in fundamental physics equations struck Gates as suspicious. Why would nature use the same techniques computer scientists use unless nature is, in some sense, computed? However, each of these potential clues has alternative explanations. Quantum space-time could be a fundamental feature of reality rather than evidence of digital structure. Fine-tuning could be anthropic selection from a multiverse, or indicate deeper physical principles we haven't discovered. Déjà vu and synchronicity could be psychological phenomena with no metaphysical significance. Error-correcting codes in physicsy equations might reflect deep mathematical structures that appear in multiple contexts for fundamental rather than designed reasons. More philosophically, some argue that certain aspects of quantum mechanics look like computational shortcuts. The fact that particles don't have definite properties until measured, that superposition allows multiple states to coexist, that entanglement provides instant correlations, all of these could be ways to save computational resources. Don't calculate what isn't being observed. Keep things probabilistic until forced to commit. Link variables directly rather than simulating spatial separation. These would be clever tricks for an efficient simulation. But again, these features of quantum mechanics could simply be how reality works at the fundamental level. Interpreting them as evidence of simulation requires already being inclined toward that hypothesis. They're consistent with simulation, but don't prove it. Perhaps the most interesting proposals involve trying to detect the limits of the simulation. If the universe is computed, there must be finite computational resources. The simulation can't have infinite resolution or perfect fidelity everywhere. There should be approximations, shortcuts, boundaries beyond which detail breaks down. Some researchers have suggested looking for these boundaries at extreme scales, in the behavior of matter at the Planck length, or in the statistics of the cosmic microwave background. In 2012, physicists proposed a specific test. If the universe is simulated on a lattice, a discrete grid of space-time points, this should create constraints on the energies and directions of the cosmic ray particles. The lattice structure would be like a crystal, having preferred directions and maximum energies. By analyzing the highest energy cosmic rays with sufficient statistics, we might detect anisotropy that reveals the underlying grid. So far, no such evidence has been found, but the energies involved are so extreme that gathering adequate data remains challenging. The problem with all these approaches is that they assume the simulators left detectable traces. If the simulation is created by a sufficiently advanced civilization, they might have accounted for beings inside trying to detect the simulation. They could patch potential glitches, adjust parameters to avoid anomalies, or even alter the simulation in real time to remove evidence as it's discovered. If the simulators don't want to be detected, detection might be impossible. This leads to a deeper question. If we can't prove or disprove that we are simulated, does the question even matter? And strangely, the simulation hypothesis connects to much older questions in religion and spirituality in ways that make it more than just a technical debate. Religious and spiritual echoes. When we examine simulation theory closely, we find it echoes, in technological language, ideas that mystics and theologians have explored for millennia. The notion that reality as we perceive it is not the deepest truth, that there's a greater reality beyond the material world, that consciousness might be primary rather than emergent from matter. These are ancient spiritual insights dressed in the language of computer science. Consider the concept of God as creator. In Abrahamic traditions, God creates the universe, sustains it through his will, and stands outside it while being intimately involved with it. This maps remarkably well onto the simulation hypothesis. The programmers would be godlike beings, creating a reality, setting its laws, potentially intervening when they choose. They would be outside the simulation, in a higher level of reality, but their creation would be completely dependent on them. Turn off the computer, and the simulated universe ceases to exist. Hindu and Buddhist philosophy's concept of Maya, the illusory nature of physical reality, parallels simulation theory almost exactly. Maya doesn't mean the world doesn't exist, but rather that it doesn't exist in the way we naively perceive it. The separate, solid, persistent things we see are actually manifestations of a deeper, unified consciousness. What we experience as matter is actually mind, or more precisely, experience is all there is, and the material world is a construction of consciousness itself. Replace consciousness with computation, and you have simulation theory. Paramahansa Yogananda, the Hindu monk who brought yoga to the West in the 1920s, described Maya using metaphors of cinema. We're like audiences watching a movie, taking the images on screen for reality, forgetting they are projections of light, or like people in a dream, believing the dream world is real until they wake. If Yogananda were writing today, he might use the metaphor of virtual reality or video games. The player forgets they're playing and identifies completely with the character on screen. Buddhist teachings about the nature of self align with simulation theory in interesting ways. Buddhism argues there is no permanent, independent self. The sense of being a separate individual is an illusion created by the process of identification with thoughts, sensations, and perceptions. What we call the self is actually a stream of ever-changing phenomena with no solid core. In simulation terms, the player character in a game doesn't have independent existence. It's a bundle of data structures and processes, a pattern maintained by computation. When you stop playing, the character simply ceases. There's no soul, no essence, just information. Gnostic traditions in early Christianity held that the material world was created by a false god, the demiurge, while true divinity existed in a transcendent realm beyond. Humans contain sparks of the higher reality trapped in the prison of matter. Knowledge, gnosis, allows escape from this false creation. This is almost exactly the Matrix's plot. The Matrix is the false reality created by the machines, the demiurge. Humans are trapped in it, unaware of their true nature. Knowledge of the truth, delivered by Morpheus, allows Neo to escape. Islamic mysticism, particularly Sufism, teaches that the world is a reflection of divine names and attributes, that physical reality is a veil hiding the face of a god, and that spiritual practice allows one to penetrate that veil and experience union with the divine. The simulated world would be a veil, literally a constructed appearance hiding the true reality of the programmers and their world. What's fascinating is that simulation theory and traditional religious thought arrive at similar conclusions through different paths. Both suggest that material reality is not fundamental. Both propose that consciousness or beings outside the physical universe are primary. Both offer the possibility of transcendence, of moving beyond the ordinary level of existence to something greater. Simulation theory is, in a sense, a tech-friendly way of expressing perennial spiritual insights. But there are also important differences. Traditional religious frameworks usually include moral structure. God or the divine is benevolent, or at least has purposes and values. The spiritual path has ethical content. There are right and wrong ways to live. Simulation theory, in its pure form, doesn't imply any of this. The programmers might be benevolent, indifferent, or malevolent. They might have created the simulation as an experiment, as entertainment, as punishment, or for reasons we can't comprehend. There's no guarantee they care about simulated beings' welfare. Moreover, traditional religion often provides meaning through connection to the transcendent. Your life matters because God knows you, because you're part of a cosmic story, because your soul has eternal value. But in simulation theory, you might be an experimental subject, a non-player character, a bit of computational fluff that exists only as long as the program runs. When the simulation ends, you simply cease. Unless, of course, the simulators preserve patterns they find interesting, uploading you to their reality, which starts to sound like salvation and resurrection. These parallels suggest something interesting. Perhaps humans have always intuited that ordinary reality is not the full story. Our spiritual traditions, our philosophical questionings, our artistic explorations of consciousness and meaning all point towards something beyond the material. Simulation theory is just the latest form of this ancient recognition, expressed in terms comprehensible to a scientific, technological civilization. But whether that recognition is insight into truth or simply a persistent cognitive bias, a quirk of how human minds model reality, remains unclear. Which leads us to perhaps the most important question of all. Does it actually matter whether we're simulated? What it means if we are or aren't simulated? Suppose tomorrow a definitive proof emerged that we're living in a simulation. Or suppose we detected an undeniable message from the programmers confirming the truth. How should we react? What would change? At first glance, it seems like everything should change. You're not really human, but a pattern of information in a computer. Your body isn't biological, but digital code. The people you love might be philosophical zombies, empty simulations with no inner life. Your entire existence is at the mercy of beings who could delete you with a keystroke. The universe could end whenever they shut down their computer. Nothing is real in the way you thought it was. But on deeper examination, maybe less changes than you'd think. David Chalmers argues that even if we're simulated, our reality is still real. The coffee you drink is still coffee, just digital coffee. Your emotions are still emotions. Your relationships still matter. Pain still hurts. Joy is still joyful. The fact that the substrate is information rather than what you thought of as matter doesn't diminish the reality of your experience. Consider an analogy. Imagine you discovered that what you thought was wood is actually a very sophisticated polymer. Your wooden table isn't really wood, it's plastic that looks and feels exactly like wood. Would you stop using the table? Would it cease to function as furniture? Of course not. It still holds your dishes just fine. Similarly, if physical reality is actually computed rather than material, it still functions the same way. The laws of physics still apply. Chemistry still works. Biology still operates. Your life continues. The philosopher Nick Bostrom points out that ethical and existential questions don't necessarily change. If we're simulated, we still want to avoid suffering, pursue happiness, treat others well, and find meaning. Knowing you're simulated doesn't make pain less painful or love less valuable. The simulation, if that's what this is, remains your lived reality. You can't step outside it. You don't have access to base reality. This is your reality, simulated or not. Moreover, the simulation hypothesis doesn't solve fundamental philosophical questions. It just pushes them back a level. If we're simulated, what about the simulators? Do they wonder if they're simulated? Is their reality fundamental, or are they also simulated by something higher? This leads to an infinite regress of simulations within simulations, turtles all the way up. At some point, there must be a base reality that isn't simulated. And that base reality faces all the same philosophical puzzles we face. Why does anything exist? Why these laws rather than others? How does consciousness arise? The simulation hypothesis doesn't answer these questions. It just relocates them. There are, however, some practical implications if we knew for certain we were simulated. We might alter our understanding of physics, looking for computational structures rather than continuous mathematics. We might approach the search for extraterrestrial life differently, wondering if other observers are instantiated at the same level of simulation or exist only as simplified background characters. We might think differently about death, wondering if the pattern that constitutes us could be preserved, backed up, or instantiated elsewhere by the simulators. We'd also have to grapple with ethical questions. If we create simulated beings, are we responsible for their welfare? Do they have rights? Would turning off a simulation containing conscious beings be murder? These questions become pressing as we develop increasingly sophisticated artificial intelligence and virtual reality. If consciousness can be simulated, then we'll become simulators ourselves, facing the ethical responsibilities that come with creating sentient beings. There's also the question of how the simulators view us. Are we an experiment? Are they studying us the way we study bacteria in a petri dish? Are we entertainment, like characters in a game? Are we students in some kind of pedagogical simulation, learning lessons they've designed? Or are we ancestor simulations, created by future versions of humanity trying to understand their own past? Each possibility has different implications for how we might relate to them and whether it's possible or desirable to communicate. Some people worry that if everyone believed we were simulated, it would lead to nihilism. Why care about anything if it's all just code? Why be moral if there are no ultimate consequences beyond the whim of programmers? But this seems to misunderstand both simulation theory and ethics. Even in a simulation, your choices have real consequences within the simulation. Causing suffering still causes actual suffering. Creating joy still creates actual joy. The fact that the universe might be computed doesn't make these experiences less real for those having them. Conversely, if we're definitely not simulated, if this is base reality and matter is fundamental, that doesn't automatically provide meaning or purpose either. We still face the same existential questions. Why does the universe exist? Why is there something rather than nothing? How should we live? What matters? Knowing we're in base reality doesn't answer these questions. It just confirms that the search for answers happens in a different kind of substrate than we might have thought. Perhaps the most important insight is that the question itself, the very fact that we can ask whether reality is real, reveals something profound about consciousness and its relationship to the world. We're not just passive recipients of experience. We're active questioners, capable of stepping back from immediate perception and asking deep questions about the nature of existence itself. This capacity for reflection, for philosophical wonder, might be more significant than any answer we find. In the end, maybe the simulation hypothesis is less a question demanding an answer, and more a koan, a paradox meant to provoke insight. Like asking, what is the sound of one hand clapping? Or, what was your face before your parents were born? The question, is this real, might be valuable not because it has a definite answer, but because struggling with it opens up new ways of understanding consciousness, existence, and meaning. Conclusion: living with the question. As we near the end of this quiet exploration, let's return to where we began. You're here, reading these words, aware of existing, thinking about existence. That awareness, that consciousness, remains whatever we discover about the underlying nature of reality. The subjective experience of being, the fact that there's something it's like to be you, persists regardless of whether you're made of atoms or bits. We've journeyed through ancient philosophy and modern physics, through quantum mechanics and mathematics, through arguments for and against simulation, through the connection to spiritual traditions and the practical implications of the question. We've seen that brilliant minds have argued passionately on both sides, that evidence remains ambiguous, that the question may be fundamentally unanswerable from within the system we're trying to understand. And perhaps that's fitting. Perhaps the mystery itself is what matters. The question, what is reality, has driven human inquiry for thousands of years. It's pushed us to develop science, to explore consciousness, to question assumptions, to peer ever deeper into the nature of existence. If we definitively answered it, what would replace it? What new frontier would call to the curious mind? Maybe the point isn't to solve the puzzle, but to live with it gracefully, to hold the question without needing a final answer, to remain open to the mystery while engaging fully with the reality we do have access to. Whether this is base reality or a simulation 17 levels deep, it's the reality we inhabit. These are the circumstances of our existence. This is where consciousness finds itself. The Zen tradition speaks of direct experience beyond concepts and theories. Before thinking about whether reality is real, there's the immediate taste of water, the sound of wind, the feeling of breath. That directness, that raw presence, remains regardless of any philosophical or scientific conclusions. The red of red is still red. The nowness of now is still now. Existence still exists. In practical terms, we can take away several insights from this exploration. First, reality is stranger than common sense suggests. Both quantum mechanics and simulation theory agree on this. The universe at fundamental levels doesn't behave according to ordinary intuition. Particles are fuzzy, observation matters, entanglement connects things faster than light. Consciousness seems woven into the fabric of reality in ways we don't fully understand. Staying open to strangeness, to possibilities beyond our current categories, seems wise. Second, consciousness remains the deepest mystery. Whether we're simulated or not, whether mind emerges from matter or matter emerges from mind, the fact of subjective experience stands at the center. Any complete understanding of reality must include consciousness, not as an afterthought, but as a fundamental feature. The question, what is reality, and the question, what is consciousness, turn out to be intimately connected, perhaps inseparable. Third, the search for truth has intrinsic value. Whether or not we can definitively answer the question of simulation, asking it is worthwhile. The inquiry itself expands our understanding, pushes science and philosophy forward, connects us to the deepest questions humans have ever asked. Even if we remain uncertain, we're uncertain with more sophistication, more nuance, more appreciation for the complexity involved. Fourth, ethical and existential meaning don't depend on metaphysics. Whether we're in a simulation or base reality, Whether we're biological or digital, suffering still matters. Kindness still has value. Beauty still moves us. Love still connects us. The substrate doesn't determine the significance of the patterns. What matters is the quality of experience and relationship, not the underlying implementation. Finally, there's a kind of freedom in accepting uncertainty. If we don't know for certain what reality is, we're released from the grip of any particular metaphysical view. We can hold our theories lightly, remain curious, update our beliefs as evidence changes. The question stays open, inviting ongoing exploration rather than final judgment. As you drift towards sleep tonight, you might let these thoughts settle gently into the background. You don't need to solve the question of reality. You don't need to figure out whether you're simulated or fundamental. You can simply rest in the fact of being, the mysterious presence of consciousness, experiencing itself through this particular perspective in this particular moment. If this exploration resonated with you, if you found value in this journey through one of humanity's deepest questions, I invite you to like, subscribe, or share your thoughts. Your support helps this channel continue exploring the big questions that make us human, the mysteries that connect us all, the wonder that keeps us reaching toward understanding. For now, though, simply breathe. Let your eyes close if they haven't already. Let the thoughts we've explored drift into the realm of dreams, where perhaps they'll continue their work in the wordless depths of unconscious processing. Let yourself sink into rest, into the simple fact of existing, into the quiet certainty that whatever reality is, you're here to experience it. The question remains. The mystery continues. And in that continuation, in that endless opening toward the unknown, perhaps we find something more valuable than any answer could provide. Good night.